What's going on, everybody? This is Mr. Diamond, and as you can probably see by my new image over here in the bottom right hand corner, I forgot my camera at home today while I'm at school recording these videos, so instead of my beautiful face gazing upon you, you will get this lovely picture down here. I can't actually tell if I'm framing it, but this picture. So I apologize for that. Next week we should be back to my camera being functional and here at the same time. All right, we are into section 4, which is complex redox, and these are going to specifically involve half reactions. And I'm sure some of you might be thinking, well, how can you have half of a reaction? Like, does that mean it only goes halfway? Like, what does that even mean? The real point of half reactions are we're trying to cut through the problem and really get to what is the most important piece in the reaction. We only care about what is actually undergoing redox, the elements that are oxidized and the elements that are reduced, or element if there's only one. To do this, we will have a reaction split into two halves, a reduction reaction and an oxidation reaction. We're just going to basically pull them apart. The quickest way to figure out what's going on for this is to work out an example. So we're going to write the half reaction for this redox reaction together. We've got CH4, two O2s, CO2, and 2H2O. Good old combustion reaction, if you remember that from chemistry. So first step, we got to figure out what is being oxidized and what is being reduced. Well, if we look at our problem here, our C has gone from -4 because our hydrogen here must be a +1. So our hydrogen being a +1 here means this must be a -4. So over here, it's with two oxygens. So this one has to be positive on this side because our two oxygens would be -2. And that means our carbon has gone from -4 to +4. That's a pretty big change. Oxidation is loss of electrons. It has lost like 8 electrons, so it was being oxidized. H has stayed +1. H is with a nonmetal on both sides, so it's going to stay a +1. And then O here is a 0 because normally our O is always a -2, but in this case it's attached to itself, so it doesn't actually share any electrons. And then over here on each of these examples, it's going to be -2. So oxidation is loss, reduction is gain. This has gained 2 electrons. That means our oxygen has been reduced. So now this is what we're going to do. Instead of stopping there and saying, aha, we have figured out what is oxidized and we have figured out what is reduced, we are now going to write an equation to represent each process. So what we should end up, if we pull out only the pieces that are involved in the actual oxidation and the reduction, you will get something like this. That carbon with a -4 charge becomes carbon with a +4 charge. Oxygen with no charge becomes oxygen with a 2- charge. Again, we're literally just getting rid of everything else that's involved in the reaction. However, we need our equations to be balanced. And while we've only ever cared about elements being balanced, we actually have to make sure our electrons end up balanced too. This is kind of a new thing that we've never really had to worry about before in this class. So to do this, you need to add electrons to the side with the higher charge so that the charges are going to actually balance out. So in this case, if we've got both of these reactions here, on the top here, this side has a higher, quote unquote, I did air quotes, but you guys can't see. I forgot I don't have a camera. This side has a higher charge. It's a +4. So we're going to need to add 8 electrons over here so that our charges will balance out. And then over on this side over here, this is higher because it's 0. We would need to add 2 electrons to get that side to balance out. And notice that our charges are balanced in this case. If you remember in class, we talked about how the charges lining up were not going to be incredibly relevant, yet this is where the charges are relevant. And there you go. We have our reaction broken down into 2 parts. We have an oxidation half reaction and a reduction half reaction. Again, the whole point here is we could look at that big thing and say, okay, CH4 and O2 were reacting. They were making carbon dioxide and they were making water. But what was actually happening as far as redox is concerned, we have honed in and specifically said this is exactly what's happening. Carbon with a 4- is turning into carbon with a 4+, and 8 electrons that will then be unattached. And oxygen is plus 2 of these electrons are combining together to make oxygen with a 2 negative charge. Now again, you might be wondering, how is this useful? Didn't we kind of already do this, just we didn't actually write it out? And it turns out there is another level to this, because when you balance a redox reaction, if you only focus on the elements, you may not have the complete story. So we actually have to make sure that the electrons would end up balanced, otherwise the reaction will not work out. So we're going to look at a simpler reaction to kind of explain this, and then I may come back to this one. I actually don't think I do in these notes, but I'll click back and I'll explain what we're talking about there. So let's look at this example here. This one's really straightforward. We're going to balance this equation. Al plus Cu2 plus gives Al3 plus Cu. Now, if you're in general chemistry and you saw this, you would go, okay, it's balanced. Like, I don't need to. It's all, there's one Al and one Al, there's one Cu. Everything is balanced. But with our redox skills, there is actually some balancing that needs to be done. So after solving, we will get these half reactions. We've split it up, and we said that Al on the left side here, again, had nothing, and on the right side had a 3 plus. We have to add 3 electrons to that side to cancel the charges, so their charges are balanced on each side. And those electrons had to have come from somewhere. And then those electrons in this case came from the copper. There was 2 electrons plus a copper with a 2 plus will make a copper that has no charge, which means that while our elements are balanced in that reaction, notice our electrons are not. This reaction is saying that you're going to put in 2 electrons, and this one says you're going to get out 3 electrons. Those don't line up with each other. And that means that we need to figure out what is actually going to, or what we need to do is figure out how many of each piece we need, so that way we can get it to be balanced out. These electrons have to be equal to each other. Now in this case, we can do that pretty easily by just multiplying the numbers. We can say, well, if I multiply this by 2, I will have 6 electrons, and if I multiply this by 3, I will have 6 electrons, and my electrons will be balanced, and we will get 2 aluminums plus 3 copper 2 plus gives 2 aluminum 3 plus 3 coppers, which probably feels kind of incorrect. Like, obviously we can't reduce all of these numbers, but like, it's just Al and Cu. Why do we need 2s and 3s? But now we know we need 2s and 3s because we need our electrons to balance. Now this is going to make a lot more sense in the attached video. If you're still like, I'm not quite sure what happened there, or you're having trouble following along, there's going to be an attached video where I'm going to actually show you writing out where all of this comes from. It's a little bit weird to explain it in person or explain it like over just the notes without actually having a piece of paper in front of me. So we'll get to that in a moment. That'll probably help make a little more sense. Okay, I'm going to stop here, but our last reaction was kind of based in electrochemistry, but for the next section of notes, we're going to look at an even more complicated reaction. We're going to try to figure out this one, and like this problem right here says, I want you to see if you can, while looking at this, figure out why this one's going to be weirder, or why this one's going to be such a problem. So, I'm going to leave you there while you think about that. This has been Mr. Diamond. If you have any questions, please shoot me an email. And please check out the attached video where I go over a more detailed explanation of how to do the half reactions and the balancing of our equations. This is Mr. Diamond, though, signing off. Have a great rest of your day, everybody.